Lecture 48, Gradient, Divergence and Curl. What is a vector differential operator, which is denoted by del? So del is what? It's in vector quantity and it's denoted by I del by del x plus j del upon del y k del upon del z. So this is an operator, differential operator. And now what is a gradient of a scalar function? So if suppose we have a scalar function phi, then I del phi upon del x j del upon del y of phi plus k del upon del z of phi is called, this is called gradient of a scalar function phi. That is, if denoted by grad, grade of phi, or we just write del of phi, that vector operator del of phi. So when that vector is operate, vector differential operator is operate on phi, we just write I del upon del x of phi, j del upon del y of phi, and k del upon del z of phi. Now here we have to note that if suppose we have a function phi, that is a scalar function, is equal to c be a surface, then del phi into del r. So suppose this is an r vector and that is in surface, then suppose this is a point P, that's in point P, and this is what? This is del r, vector del r. So the perpendicular normal, obviously normal on that surface, and this is a surface phi, this is a surface phi. So this is what? This is the vector normal n, and this is what? This is a gradient of that surface phi. So here phi, suppose we have say the phi be the surface, then del phi into dot del r is equal to 0. That is, del phi is the perpendicular to every that vector del r lies on that surface, and del phi is the normal to the surface phi, that normal to the surface phi. So here it means that the gradient of a scalar field phi is a vector normal to the surface phi, and the magnitude is equal to the rate of change of phi along to this normal. So you have to remember, if we take the gradient of a scalar function, so we get a vector quantity, the first one, and that vector quantity represent the normal to the surface. Now the directional derivative. So here the directional derivative, the component del phi in the direction vector d is given by del phi dot vector d. So this is called the directional derivative of the scalar point function, that is phi, in the direction d. Now there are some properties of the gradient. If suppose phi is a constant scalar point function, means that scalar function is a constant, then the del operator, when we operate on the phi, we get 0. Now if suppose we have phi 1 and phi 2, we have two scalar point function, then if we have given phi 1 plus minus phi 2 and we have to operate the del operator on that, so that operator is operate separately on the both. So we write del phi 1 plus minus del phi 2. And now if we have the product of these two scalar function and we have to operate del operator, so here we follow the product rule of differentiation. Like the product rule of differentiation means the first function, that is phi 1, and we operate the del operator on phi 2 plus phi 1, sorry, phi 2, and del operator on phi 1. Similarly, if we have the two function are in the form of fraction, that is phi 1 and phi 2, and we have to operate the del operator, so here we follow the product the quotient rule of the differentiation, like that is phi 2 same, and the del operator operate on phi 1 minus phi 1 same, and the del operator on phi 2 and divide by phi 2 whole square. Example, find the angle between the surfaces. We have given two surfaces, we have to find the angle between them at that point. So if you want to find the angle between the two surfaces, so we find the normal of these surface at that point. So we can say you have to remember angle between two surface at a point is what is the angle between the normal to the surface at that point. Now we let the two surfaces, that is phi 1, this in phi 1 we can write x square plus y square plus z square minus 9, and the another surface we take phi 2, that one we can write x square plus y square minus z minus 3. Now because we have to find the normal of that surface and normal of these surfaces, so we take the gradient of phi 1, that is del of phi 1. It means I del upon del x, j del upon del y, and k del upon z of phi 1. Similarly, we find the gradient of phi 2, that is delta phi 2 means I del upon del x plus j del upon del y plus k del upon del z of phi 2. Now the gradient of phi 1 is what? We operate the del phi 1 function on first, so means take the partial derivative with respect to x, so we get 2x, so write 2xi plus, now the second term, so we get the partial derivative with respect to y, so we write 2yj and 2zk. So this is what? This is a normal to the surface. So the similarly we find the gradient of phi 2, so we get the partial derivative of x of phi 2 with respect to x, because we operate that function, so we get 2xi plus 2yj, and the derivative of z is minus 1, so we get minus, this is minus k. So this is the gradient phi 2. Now these are the normal, so the normal, we say the normal at the given point, and the given point is what? 2 minus 1 2. So we take, this is say n1 or eta 1 at point 2 minus 1 and 2, we substitute on the place of xyz, so we get 4i plus, sorry, this is minus 2j and plus 4k. Similarly, same for the, we take the eta 2 at the point given point, which is 2 minus 1 and 2, so we get 4i plus, sorry, again minus 2j and minus 2k, sorry, only k, that is k. Now we find the angle between the vector, and you hope you all of you know the formula. Angle between two vectors is what? Is vector 1, that is n1 into vector n2 divide by the magnitude of n1 dot magnitude of n2 is equal to what? Cos theta. So if we take the dot product of these two vectors, so what we get? 4I dot 4I, all of you remember I dot I 1, j dot j is 1, and k dot k is 1. So what we get? 16 plus 4 and 4k dot 4 minus 4 divide by, now take the magnitude of the n1, so we get under root 16 plus 4 plus 16 into the magnitude of n2 is 16 plus 4 plus 1 is equal to cos theta. So we get cos theta is equal to 16, that is 36, 6 root 21, or we can write, this implies theta is equal to cos inverse 8 by 3 root 21. So that's the angle between these two surfaces which is passed through at that point. In that way you can easily find the angle between two surfaces. Here we use the help of the gradient. Gradient shows the normal of the vector surface. To find the directional derivative of a function, we have given a function 2x square plus 3y square plus z square at that point 2 1 3 in the direction of the vector a, that is I minus 2k. So here the function is given, which is a scalar function, and we have to find the directional derivative. So for the directional derivative, first we have to find the gradient of that scalar function, scalar point function. So first we find, we have given the function is what? Fx xyz is 2x square plus 3y square plus z square. Now we find the gradient of f, that is del of f. Here f is a scalar point function. It means I del upon del x plus j del upon del y and k del upon del z of that function f, and the functions operate on that, so we take the derivative with respect to x, with respect to y and z. So we get 4xi 6yj and 2zk. Now this is the gradient of f, the gradient of f. Now at point, because we have to find the rational derivative at that point, so on 2 1 and 3, so we get the gradient of f is what at 2 1 3. So 4 into 2, that is 8i plus 6 into 1, that is 6j plus 2 into 3, that is 6k. So that is, we get the gradient of f at that point. Now because we have to find the directional derivative, this is also we write del of del of f, the function is f, we write f. So the directional derivative of f function in the direction, and the direction is what? That vector, that is a vector I minus 2k. Now because we have to find the direction in that vector, so we take the unit vector of this. So the unit, first we find the unit vector of a, is what? A unit vector, vector A, and the magnitude of vector. So here we get I minus 2k upon root 1 plus 4. So we get the unit vector I upon root 5 minus 2 upon root 5 k. Now this is the unit vector A. So the directional derivative of f in the direction, that direction, here we write the gradient of f dot the unit vector, or you just write del of f a cap, that is the unit vector. So this is the gradient 8i plus 6j plus 6k dot the unit vector, that is I root 5 minus 2 upon root 5 k. Now I dot I, as we know, 1, so we write 8 by root 5, and the j dot j vector is not present here, so 6 k dot k, that is 1, so we write minus 12 by root 5, and finally we write root 5 and upon minus 4 upon root 5. So this is the directional derivative of that function f in the direction this at that point. So in that way we use a gradient. Next example, find the unit normal vector of the cone of revolution z square equal to 4x square plus y square at the point 1 0 2. Now here the given surface is what? Is a cone. So the given surface, we take the surface, we say phi is what? 4x square minus plus 4y square minus z square. So we have given a surface, and first we find the normal, and if you want to find the normal vector, so we take the gradient of that surface phi. It means del of phi, that is I del upon del x plus j del upon del y and k del upon del z of function phi. Now that function phi operate on this, so we write I del upon del x of phi, j del upon del y of phi, and k del upon del z of phi. Now the derivative of phi with respect to x, we get 8x, the vector I, and the derivative with respect to y, we get 8yj, and the minus 2zk. So this is what? This is the gradient of phi. That is, we can say this is the normal vector, or we say n1. Now at point, the normal at point, the given point is what? 1 0 2. So n1 at that point is 8 into 1, that is 8i, 8 into 0 we get 0, and 2 into 2, that is minus 4k. So this is the normal vector. Now because we have to find the unit normal vector, this is what? This is a normal vector, and we have to find the unit normal vector. So we take eta cap, that is what? The vector eta 1 and the magnitude of that vector eta 1. So here we get 8i minus 4k, and the magnitude of that is 64 plus 16. So we get 8 by that is 80, and the 80 we can write 4 root 5 I minus 4 upon 4 root 5 k, or simplify we write 2 by root 5 I and 1 by root 5 k. So this is what? This is the unit normal vector for that surface.